Hi, everyone. Yeah. Hi, everyone. My name is Emily Ferracci,
And I'm Aditya.
and we're members of AXE Lab at the University of Chicago, and today we're very excited to present CARDinality, interactive card-shaped robots with locomotion and haptics using vibration. So, cards are a prevalent part of our daily lives. We use them for a variety of things, from play, transportation, divination, membership, to even our very own identity. And when we think about why that is, there's something about the form factor of cards that has a lot of benefits in terms of interaction design. Cards are portable, they're planar, they're very thin, and they can also carry specific symbolic meanings that are very helpful for communication and interaction. And with this research, we wanted to ask the question of what if? So what if, when you're doing online shopping and you're spending a little too much money, your cards could know that and run away from you? Or what if, when you get locked out of a specific room, you slide underneath the door to come find you? Yes. So we wanted to reimagine what cards could be using actuation. And specifically, we wanted to broaden the design space of existing traditional cards. So when we think about the way that we use cards already, there's both on-table and in-hand modalities. And those are the two main ways that we interact with the card form factor. And what happens if you add actuation? So when a card is on table, actuation, in our case, enables locomotion and also notifying users through buzz notification. In hand, it allows for a variety of vibration haptic patterns that are also very helpful in interaction design. But we didn't want to stop with actuation. By adding sensing, we're also able to broaden the interaction space, specifically knowing the status of a card, whether it's in hand or on table, but also events like taps, flicks, or orientation. And it doesn't stop here either. There's also in deck, in pocket, in wallet, and all the ways that you probably use cards in your daily lives. And so with regards to prior works in this domain, there's been a variety of prior explorations, including robotic tangible user interfaces with material form factors like post-it notes or lines, but also things like interactive cards and using external actuation in order to move passive card mechanisms around. But with our work, we wanted to use actuation fused into a thin, card-like form factor. And we also wanted to create a fully embedded device that had locomotion, haptics, and wireless sensing. And while some of these do it individually, none of them do it all together. And so we set specific design criteria so that we could create iterative prototypes that would lead us to our final hardware design. So what do we need out of this mystery card? First, thin card-line form factor. That was a very important part. But also embedded actuation for both locomotion and haptics, encapsulation of actuation to facilitate customization, and finally, fusing sensing and wireless communication so that it could be a portable device and have certain interaction. So that leads us to our hardware prototype, CARDinality. So we talked about thin, but how thin is this device? Aditya here pulled it out of his wallet. Essentially, the device is 1.3 millimeters at its thinnest and 4.7 millimeters at its thickest part with a PCB and motor. Also, Kane is showing it in the middle here. We created a device with embedded actuation for locomotion and haptics. And the way that we do this is by using vibration, and specifically 4 vibration motors on a card-sized PCB. And we'll explore specifically how this works later in our slides. We also encapsulate that actuation in order to facilitate customization, so things like an optional 3D motor casing, and because it's vibration, it can transfer, and we can still customize the device and still have the elements that we wanted out of it. And finally, fusing sensing and wireless communication. By having an onboard IMU, we were able to detect specific interactions and also have a Bluetooth, be able to connect the device to Bluetooth software, which we'll talk about right now.
So how do we achieve this? Vibration has been used as a form of actuation for locomotion in prior works such as rat chair and kilobots. However, in these approaches, vibration is done through an inching matter, due to the fact that these devices have legs. In our device has no legs at all, and this allows for omnidirectional vibration-based sliding locomotion. Since there are no legs, the device is not mechanically biased to a certain direction, and the shifts in center of mass of the device allows the robot to appear like it's sliding. How we achieve this is we constructed a training setup where we attach an Heroku marker on the robot and a camera on a training rig and collect data by observing different motor patterns. So in this process, it takes around 2 hours based on our cursor. So after we obtain the results of the training process, we filter down the results to 36 different directions that represent omnidirectionality. This is, of course, done for the other side as well, and this also allows for some degrees of error in our device, since this is a novel locomotion approach. So in our results, we first test using some random data, which of course doesn't work, random parameters. We also test on multiple robots, and we first test by transferring the parameters from one robot to another, and we also use the individualized robots results. And what we find is that an individualized training process is required and works best for this approach. In our paper, we also delve into further experiments. So one experiment that we looked into is robustness, where we run the same parameters found multiple times and find the distribution of speed and accuracy. We also test transferability, where we test this robot on different surface materials and customizations. Details can be found in section 6 of our paper. Now that our device is implemented and trained, we can introduce some novel applications using actuation. So our first application is augmenting CARDinality. So here, actuation is used to signal, provide haptic feedback, and also as a means to navigate through the 2D space of the Another application is learning tools. So using sensing, material sensing, the device can be placed on different materials and locomotion to press them. So in this case, the user knows the word. So the device to back to the other. And we also can use actuation as a means to verify as a payment has been processed. And of course, there's many other applications that we've explored in our paper. In conclusion, we present a novel hardware, a card-shaped robot with vibration-based actuators and locomotion for locomotion and haptics with integrated sensing. We also developed a novel locomotion gate, which is the omnidirectional sliding locomotion and the peripheral training setup to achieve this. Lastly, we also introduced a range of applications that demonstrate the unique interaction capabilities of CARDinality. So, things that we wanted to explore. The battery life of this device is only around 2 hours, and one thing that we explored is attaching a wireless charger in the bottom side of the battery, and we verified that this worked. We've placed a wireless receiver in the bottom of it, and the device does indeed charge. The issue is that this does add thickness to the device. The reason why we think we need to personalize the device is that the fabrication process creates non-uniform devices due to warping. So by creating a more unified approach, we can ease up and create a more generalizable model for locomotion across devices rather than personalize every single time. We also explored different hardware configurations by varying the thickness of the PCB and also the motor placements in the device itself to learn more about the physical model of the robot. And lastly, in the space of interactions, we've only focused on in-hand and on-table interactions. And we've met up with a magician here at UIST, actually. And cards and cards can be used for a variety of different interaction spaces that we didn't fully explore in this paper. And this is the team that did CARDinality. We would like to acknowledge other members of our lab. And yes, I'm looking for a PhD position. Emily and Kane are also looking. And thank you so much for attending our talk. We have a demo tonight at stand 1021. And we also have a poster.
Thank you.
Thank you so much.
Cool. We'll have time for one question. Is there anybody? Or you can also raise your hand and then, oh, there you go.
Hello, really cool talk. My name is Devyani McLaren. I'm from the University of British Columbia. I'm a PhD student in the Spin Lab. Long intro. I guess my question is, who looks at a card and says, what if it moves? What was kind of the inspiration for this project?
Yeah, that's a really good question. So the project kind of started from BristleBots. So it's like small kind of play devices that use vibration to move around. And we were really interested in those kind of, those interactions as play. And then that kind of extended to using vibration for locomotion and how the card form factor can actually fuse those two together, both the idea of play and the idea of vibration for locomotion. So yeah.
Cards. Cool. Thank you.
All right, cool.